Section: Introduction. In this section, we explore the xLSTM, which serves as the foundation for our xLSTM 7B model. The xLSTM cell is designed to be fully parallelizable, allowing for efficient training of large models while ensuring quick recurrent inference with consistent memory usage. During the inference phase, when we generate tokens, the xLSTM cell processes a sequence of input vectors over time steps in a recurrent fashion. It transitions from one state to the next based on the input it receives. In this context, we have the hidden state representing short-term information, the cell state for long-term memory, a normalizer state for scaling, and a max state that regulates the input gate strength. In the generation mode, the xLSTM cell updates its states according to specific equations. The gate activations are calculated, and we derive the query, key, and value vectors from these activations. The input and forget gates are determined from pre-activations, while the output gate is computed using a sigmoid function. We can use either RMS norm or layer norm for the normalization layer. Section Summary. In this section, we present the xLSTM architecture, which utilizes xLSTM cells for efficient large-scale model training and fast recurrent inference, maintaining constant memory usage. We detail the generation mode of the xLSTM cell, highlighting its state update equations and gate activations, which enable effective token generation during inference. Section: Training Mode. In this section, we describe our training mode for the xLSTM cell, which processes a complete sequence of input vectors and calculates hidden states for all time steps simultaneously. We refer to this parallel processing as the xLSTM cell in training mode. Thanks to the linear nature of the recurrence, we can compute hidden states in chunks without needing to store intermediate memory states. This chunkwise approach allows for highly efficient training, similar to flash linear attention, and outperforms flash attention in speed. For more details on this training method, we direct readers to our previous work. Next, we introduce the multi-head xLSTM, which is akin to multi-head attention in transformers. Our xLSTM features multiple xLSTM cells, and we concatenate the hidden states from each head before projecting them again, forming the xLSTM layer. We will discuss how to choose the number of parallel heads in a later section. We also present our xLSTM 7B architecture, which is designed to tackle three key challenges: creating efficient architectures for inference, ensuring effectiveness in large-scale pre-training, and achieving stable convergence. Our xLSTM 7B meets these requirements by being efficient during training and inference while maintaining stable convergence. We will elaborate on our architectural optimizations for both training and inference in subsequent sections, particularly focusing on the gating mechanism of the xLSTM cell. To optimize for efficiency, we revisit the design of the xLSTM cell, which is central to the xLSTM 7B architecture. In previous designs, the xLSTM cell was combined with channel-wise convolutions between linear up projection and down projection blocks. This setup, while effective for language modeling, resulted in high computational costs and GPU memory usage due to operating in a higher dimension than necessary. Additionally, the absence of position-wise feed-forward layers reduced the efficiency of linear operations. The previous architecture also included extra components that led to inefficient GPU utilization and increased communication costs during large-scale training. To enhance the xLSTM block's efficiency, we now operate the xLSTM cell within the model's embedding dimension and place position-wise feed-forward layers after each xLSTM layer. This change boosts the efficiency of linear operations and reduces computational costs, allowing for larger batch sizes during training. We refer to this new configuration as the post-up projection block. We also eliminate unnecessary operations like channel-wise convolutions and replace block-wise projections with dense linear layers, further increasing efficiency. Moreover, we compute gate pre-activations for each head independently, enabling us to apply model parallelization strategies similar to those used in transformers. These optimizations lead to a significant speedup in training for our 1.4B models, with only a minor trade-off in validation complexity that can be addressed with additional training steps. Although the new block structure reduces the size of the xLSTM cell's memory states, we find that it does not negatively impact the language modeling quality of our model. Section Summary. In this section, we describe our training approach for the xLSTM cell, which processes input sequences in parallel to enhance efficiency, and we introduce the optimized xLSTM-7B architecture designed for effective inference and stable convergence during large-scale training. We also detail our modifications to the xLSTM block, which improve computational efficiency and reduce memory usage, resulting in a significant speedup in training without compromising language modeling quality. Section: Optimizing the memory capacity. In this section, we focus on optimizing the memory capacity of the xLSTM. The total memory capacity relates to the size of the memory cell states stored in GPU memory. By selecting either the number of heads or the head dimension, we can determine the other based on the embedding dimension. For our xLSTM-7B, we set the parameters accordingly. We calculate the total memory state size in bytes, assuming the state is stored in a specific format. We present the memory state sizes for various head counts and discuss their trade-offs regarding language modeling performance and training efficiency. We opt for 8 heads with a head dimension of 64 for the xLSTM-7B to ensure the model has sufficient memory. Next, we discuss the fused generation kernels for the xLSTM cell. During autoregressive generation, we compute the hidden state outputs using a recurrent formulation that involves several operations. Each operation typically requires separate GPU kernels, which can slow down memory operations. To enhance efficiency, we create fused GPU kernels for the xLSTM generation mode, resulting in faster generation times. We also address stability issues we encountered with the previous xLSTM architecture at the 7B parameter scale, particularly during early training stages. We observed that higher learning rates caused significant spikes in gradient magnitude and loss values, often due to large outlier features. To tackle these stability problems, we implement several strategies, using RMS norm instead of layer norm, applying soft capping to the input and forget gates, and initializing the input gate bias with negative values. We find that replacing layer norm with RMS norm at the input of each layer improves training stability, confirming this through our experiments. To manage large outlier features, we apply soft capping to the input and forget gate pre-activations, ensuring their values remain within a specific range. This adjustment significantly enhances the stability and performance of our xLSTM architecture. Additionally, we apply soft capping to the final layer logits. We also note that initializing the input gate with large negative values helps reduce gradient norm spikes early in training, which positively impacts model performance. Our optimizations lead to stable pre-training of the xLSTM-7B, as illustrated in our figures. We provide a detailed block architecture of our xLSTM-7B and our training recipe in the appendices. In terms of related work, while most large language models have relied on transformer architectures, we see a growing interest in recurrent and hybrid models for their efficiency in handling long contexts. Recent efforts have focused on the 7B parameter scale, balancing model capacity with resource constraints. Notably, Griffin was one of the first hybrid recurrent models trained with up to 14B parameters, followed by recurrent Gemma with 9B parameters. The Griffin architecture employs a specific convolution before sequence mixing, while Eagle 7B builds on the RWKV architecture with a matrix-valued hidden state. Among the Mamba models, a comparative analysis showed that hybrid architectures can outperform transformers, leading to the development of new hybrid models like Samba, Zamba, and Jamba. More recently, Falcon Mamba and Codestrel Mamba have demonstrated that purely recurrent architectures can exceed the performance of both hybrid models and transformers. Section Summary. In this section, We optimize the memory capacity of the xLSTM by adjusting the number of heads and head dimensions to enhance language modeling performance while ensuring stability during training through techniques like RMS norm, soft capping of gate activations, and negative input gate bias initialization. We also discuss the advantages of our architecture compared to recent hybrid models, highlighting its efficiency in processing long contexts. Section: Experiments. In this section, we begin by benchmarking xLSTM-7B against leading transformer and recurrent large language models, LLMs, that have 7 billion parameters. We assess its performance on the Open LLM Leaderboard V2 using the LM evaluation harness. Our findings, summarized in a table, indicate that xLSTM-7B ranks in the middle among 7B models, many of which were trained on significantly larger datasets. We believe that with a more extensive and better curated training dataset, particularly with a focus on math and code in the early training stages, xLSTM-7B could achieve performance comparable to the top 7B models. Next, we evaluate long context capabilities using the ruler benchmark, which includes various tasks with context lengths ranging from 4,000 to 131,000 tokens. We analyze both the standard xLSTM-7B and a long context version, xLSTM-7B LCTX, which incorporates a modified cooldown phase. In this phase, we add long context data to the training set and train the model with a context length of 32,000 tokens, adjusting the batch size accordingly. We compare our results to Llama 2, not fine-tuned for long contexts, and Llama 3.1. Fine-tuned for long contexts up to 131,000 tokens, as well as other models like Llama and Mamba. Our results show that Llama 3 performs best due to its extensive fine-tuning, while Llama 2 struggles with context lengths beyond 4,000 tokens. For xLSTM-7B, the long context training significantly enhances its capabilities, allowing it to perform competitively against state space models and surpass RWKV 5/6. Notably, xLSTM-7B achieves an average accuracy of 20% at a context length of 131,000 tokens, despite being trained only up to 32,000 tokens during the cooldown phase. This is impressive, especially since xLSTM-7B must manage all information in a fixed-size memory, unlike transformers that can expand their memory. We think that further training on longer sequences and a more advanced fine-tuning approach, similar to that used for Llama 3, could enhance xLSTM-7B's performance. In terms of speed benchmarks, the fixed memory size and linear scaling of our xLSTM architecture allow for efficient generative inference in both large-scale environments and on edge devices. We focus on local single-user inference, which is typical for edge device deployments. We benchmark xLSTM-7B on a single NVIDIA H100 GPU with a batch size of 1, comparing it to Llama 2, Llama 3, and Mamba models. We utilize implementations from the Hugging Face Transformers library and optimize them with Torch, Compile and PyTorch CUDA graphs. For generation throughput, we measure the speed of text generation in tokens per second at different prefill lengths. Our observations reveal that transformer models experience a significant drop in generation speed with longer prefill lengths due to the quadratic scaling of their attention mechanism. In contrast, recurrent architectures like xLSTM-7B maintain a constant generation speed regardless of input context length. We find that xLSTM-7B is approximately 50% faster in text generation than Mamba, primarily due to our optimized block design, and it outperforms Llama-based models at a prefill length of 0. Finally, we assess token generation time and GPU memory usage without prefill for various generation lengths. Our results illustrate the linear scaling of recurrent models compared to the quadratic scaling of transformers in terms of runtime. Additionally, we note the constant memory size of recurrent models versus the linear growth of the transformer KV cache. Llama 3, which uses grouped query attention, has slower memory growth than Llama 2, which employs standard multi-head attention. Thanks to our optimized block design, xLSTM-7B operates in a lower dimensional space, resulting in a significantly reduced memory footprint and faster generation times compared to Mamba models. Section Summary. In this section, we benchmarked xLSTM-7B against leading 7B parameter models, finding it ranks mid-range but could improve with better training data. We also evaluated its long context capabilities, demonstrating that our model outperforms some baselines in efficiency and speed, particularly in generating text, while maintaining a lower memory footprint compared to transformer models. Section: Time to First Token. In this section, we focus on the response times of our language model, which is crucial for applications where it serves as an interface for users, especially on edge devices. We measure the time it takes for the model to generate 1 or 100 tokens after processing different prefill lengths. Our xLSTM-7B model consistently shows the fastest response times across all prefill lengths. Next, we assess the prefill throughput, which is the number of tokens generated per second for a total of 65,536 tokens, varying the batch size and context length. We observe that the throughput of the Llama models decreases with longer contexts due to quadratic scaling. In contrast, our xLSTM-7B maintains the highest throughput, approximately 70% better than Codestral Mamba, regardless of context length. We also conduct ablation studies to confirm our design choices aimed at enhancing the training stability and efficiency of the xLSTM-7B architecture. We compare the pre-up projection block with our optimized MLSTM block, focusing on validation perplexity and training step time across 3 model sizes. Both architectures utilize gate soft capping and specific input gate bias initialization. The results show only a minor difference in validation perplexity at the largest model size, but we achieve a significant speedup in training step time, validating our choice of the post-up projection block in xLSTM-7B over the pre-up projection used in Mamba and earlier xLSTM designs. We investigate how the memory state size, influenced by the number of heads, affects the performance of the xLSTM in terms of validation perplexity and downstream tasks. We train xLSTM models with 7 billion parameters and various head counts on 160 billion tokens from our pre-training dataset. Our evaluations indicate stable performance across different head counts, with slight improvements for more heads, particularly at 16. However, our long context evaluations suggest that using 4 and 8 heads yields better results for very long contexts. We believe that further studies with larger datasets would be beneficial to explore this relationship more thoroughly. Regarding the normalization layers in our xLSTM block architecture, we implement a pre-norm at the block entry and a head-wise norm layer after the MLSTM cell. We test the impact of different normalization types, specifically layer norm and RMS norm, on training stability and performance. Our findings confirm that RMS norm significantly stabilizes the pre-norm, while the choice of norm type for the MLSTM cell state does not affect stability or performance. We also highlight the importance of soft capping the output logits and the input and forget gate pre-activations for training stability. Our visualizations show that runs without soft capping exhibit higher variance in gradient norms and poorer validation loss. Lastly, we initialize the input gate with larger negative values to reduce spikes in gradient norms. We test the effect of making the input gate non-trainable by comparing a fixed input gate version with one that maintains our low default initialization value. While the learnable input gate shows only slight performance improvements on standard downstream tasks, it significantly enhances performance in long context evaluations.